Today we want to review the exercises at the end of chapter, for chapter 9, and we will probably have a little time left over after that, in which case we will look at a couple of details from Tuesday's lecture that I didn't have time to review. Some interesting properties of the examples that we examined there. Let's start then with the exercises from the end of chapter. And if you're having trouble with audio or video, please type something in the question box, which I will be monitoring. Make sure I have that pulled up here real quick. So the assignment was really an integrated assignment. There are 6 steps really, but it's all the same problem, or can be thought of as the same problem. We have this function here, sort.my, and it sorts a data frame by levels in an index. We're supposed to use traceback and debug to see why the second example doesn't work. So we'll put that off to one side for a minute. Let's grab that code. And for now, I'll put it down here at the end of my examples, just as a starter point. So we source this function, and it sorts a data frame by some index. So we try the first example. That seems to sort fine. It's the off, and I'm actually not sure if it actually did anything. Yeah, probably it did. 6 is now up front. I think 1 was before, if you say head the off. Yes, so working nicely. Let's try the second example where we take a reduced data frame and we sort it on subject again. And we get an error. Excuse me. So we're wondering to ourselves, what is going on here? Let's go ahead and execute traceback to see if we can find out which function was operating when the error occurred. It turns out to be a very short stack of functions. There's only one element. It was in fact the function we wrote that returns the error, and not something that our function called. So that limits our options. We still have this. We can debug our function. Of course, having said debug, we have to relaunch the code, or some example of it. In other words, recreate the error with debugging turned on. We've done that, and now we are inside the function as it is evaluating the call that we passed. Let's see what we have for objects sitting around. Okay, there's an index. No surprises there. That's just a subject that we passed in. There's also X. Oh, wait a second here. We were expecting that X was a data frame, right? This is a function that sorts data frames. But here we see that X is really just a numeric. That's the problem right there. It doesn't make any sense to sort a data frame or to sort on some index if in fact what you were working with wasn't even a data frame. That is, we have a function designed to accept data frames, but we passed it some other kind of object. So what we need to do then is trap the error where we get the wrong object type. That's what we do if we really wanted this function to be robust and well-formed. Right now we're just going to quit out of this and go ahead and delete the rest of that code that I added to this script because we don't need it anymore. We're going to carry on with question 2 from the examples, which does about the same thing. It says modify sort.my so that it sends a message if X is a matrix, warns if index is not as long as n row X, and stops if X is not a data frame or a matrix? Well, great, you get to use all your knowledge about warnings and errors and messages. You're also testing the past arguments to make sure that they conform to your expectations for sorting. So I've done that up here in this example. Actually, this is a single function definition that answers all the exercises listed in that block. So here I send a message if X is a matrix, message X is a matrix, profound, and if X is not a data frame or is, if this is not true, and what I'm testing is everything between the two parentheses here, that either X is a data frame or X is a matrix. If that's not true, we're going to stop and report that this function only works for data frames and matrices. Looking again at the exercises, that covers all of number 2. Now we're going to say modify this function so that if index is a length 1 character vector, it is assumed to be a column name in X. That gives the user some flexibility. They could have passed a real index here for index, or they could just name one of the columns in X that should be used as the index. For example, subject, right? So what we've done in here is we check if index is character, then we're going to make sure that the length of index is 1. That is, we've got a length 1 character vector, so just a scalar word, if you will. And if all those are true, then we're going to go ahead and let index be reassigned as that column in X, which has that same name. For example, if you passed in subject, the word subject in characters, then now we've got X dollar subject, essentially, as our index. Now we go ahead with the usual part of the function. Actually, not quite yet. We're going to build in some detail from step number 4, which says modify this function so that it rounds every numeric column to 2 significant digits. Well, that's not really very challenging. We do that right here. For column in names of X, that is, take each column name in turn, and then see if that column inherits the word numeric. That is, if that column is of class numeric. And if so, then we're going to reassign the value of that column using the subset operators or the element select operators. And we're going to take the column itself and call signif with a digits of 2 just to trim everything back to a very readable version of the original data. Okay, we won't show that happening just yet. We're going to show this all at once at the end. Question number 5 says, modify sort.my so that the result is invisible. And then we ask ourselves rhetorically, what use is an invisible result? Okay, so we modify it right down here where we do the indexing as per usual, we do the ordering as per usual, and now instead of returning X, we return invisible X. And that's going to give a strange result on screen. You'll call this function, you won't see anything. That's mostly for demonstration. You wouldn't usually do that with a function of this sort. The utility of returning something invisible is that it can still be assigned to some value. Or sorry, assigned to some object name. You would probably use invisible for programming needs where you don't want material arbitrarily appearing on screen. But it doesn't mean you get nothing. You still get something invisibly that you can assign to an object name. Well, at least in principle, we've satisfied the demands of numbers 1 through 5. Let's see about number 6. Number 6 says reclassify Theof as an object of type MI. It's still going to be a data frame, but now it's going to be a MI data frame. This will be the class vector. And then we're going to sort it using a generic function. That's all about object orientation, the last topic from chapter 9. We'll handle that part separately. So we'll put the book away and start trying some things. We're on the command line over here. We're going to select all this material and run it. So now we could type sort.my, see that it has the new definition. Now we can try testing our function to make sure it satisfies the expectations articulated in the exercises. So we'll try this one right here, sort as matrix. We'll run that. And we get a message that X is a matrix. Great, that's just the behavior we intended. We'll call the same function, and this time we'll try the case where index is just the name of a column in X. Let's run that. And there are no errors, that's good. We do get a warning that index is not as long as n row X. And you know, probably we should rewrite this function so that we don't get the warning in that case, because this is exactly one of the intended supported uses of this function. It's a use that we intended to support, where you just pass in subject. So it doesn't really make sense to give a warning here. You'd want to give the warning when somebody meant to have an index element for every row in the data frame, but accidentally grabbed the index from the wrong location and it's too short by a few, or it's only a couple of index values or something like that. So in this case we didn't really need the warning, but at least we see the warning is working and this indexing is working. We can modify this slightly to make it visible again. Well actually that proves that our invisible thing is working, because you don't see the result here. If you wrap this in parentheses, then suddenly it will be visible. And actually, to make it a little more readable, we could just stick head out in front and only see the first little part. Subject 6 appears first because it sorts first in an ordered factor. And that's good. And we see we're getting the expected results. Let's revisit that error. You remember that when you take Theof conc, you don't get a data frame, you get a vector. Now, actually, this is just a side topic, but you could force this to be a data frame by saying drop equals false. By default, the subsetting on a data set, on a data frame, will drop unused dimensions. So if you have basically a one-dimensional return value, it gets converted to a vector instead of being returned as a factor. If we do this, then we actually get a very, very narrow data frame. Let's go back to the top of that. And it's just a one-column data frame. Perfectly legal, but that's substantially different from being a vector. So when we tried this before, we got an error. Now we'll try it this way, and we do get an error, but at least now we have an informative error. It says X must be a data frame or matrix, and that's a good behavior to have. That puts the burden on the user to go back and do the drop thing, drop equals false, or find out what it was they had intended and fix the problem. Now we move on to the object orientation aspect of this problem. You know that Theof already has a class. We can display it just by supplying that material. And it's a rather complicated class, but it does depend on data frame at its root. We're going to reassign the class. We're going to call it class my data frame. Now remember what this does, because sort turns out to be a generic function. If we just type sort over here, we see its definition, and it's pretty short, and it has those very important words, use method, sort, right in there. What happens in this case, as a reminder, is that R will take X, figure out what its class is, and then look for something called sort dot whatever that class was. Well, let's go ahead and look up what that class is for Theof. And of course, we've just changed it. Now you can't really dispatch on all of these at the same time. By default, R will just look at the first one and say, okay, what I'm really looking here for is a function called sort.my. Is there such a thing? Yes, there is. We've defined it. There are a bunch of others as well. You could look at all the methods for sort, and you see that right now there are only 3. There's a sort method for POSIX LTs, there's a sort method which is default, and there's the one we just defined. That's the one that will be invoked, or if you will, that's the method that will be dispatched when we try to sort an object of class my. So we take this code right here with index as subject, and we run it, and we get the behavior we saw before. Again, a warning about the index not being as long as expected, but there are no errors. That's good. And we didn't say sort.my, although that is exactly the function that was dispatched. So this is classic object-oriented behavior, and instead of just letting R provide it, in this case, we made it happen. That's a useful technique in many programming circumstances. Are there any questions about the exercises from the end of chapter 9? I'm going to revisit the script we were working on Tuesday. Before I go, I'll point out that advancedfunctionsexercises.r is already posted on the course website, so you can download it there. Right now I want to go back to these functions and add some supplemental material to some of the examples. In section, let's look at section 9. What's a good place to put this? Maybe 9:15 is fine. We defined a function called deviation, and then we tested it to make sure it's actually working. Looks good. Deviation had an error message. It tests if not is numeric x, stop, and then say x must be numeric. So if you said something like deviation subject, you should get an error. That's nice. If you have a lot of function arguments, we don't, but supposing you did, it might take you quite a few lines of code to test each one of them in several different ways and write custom messages for each of them. R provides a shortcut in that case, which I like a lot. We could just take out this line of code, for instance, and write this instead. Stop if not. Now we get to give a comma delimited list of arguments. For example, stop if not is numeric x. And that does the exact same thing as the line of code we had before, but in this case, the message is automatic, and you don't have to spend time writing it. Also, you can chain these together. I don't know what else we put in here. Let's see, x should be numeric. I think we could test whether the length of x is greater than 0. That would make sense, because you really can't take a meaningful mean if you don't have any values. In fact, the whole function would not be very interesting if you had no values. So let's define it that way, using stop if not, and two test conditions separated by a comma. There's a problem here. I must have missed something. Let's step through my code real quickly, see where it occurs. Oh, I have all this else if stuff in here, and I have no if anymore. So I can just take out one of the else's to give the warnings. We're not really worried about those warnings right now. We're just trying to demonstrate the use of stop if not. That was almost good, except we seem not to have completed the function somewhere. Stop me if you see it. We'll try this one line at a time. Always a good strategy. Do the comment as well. Still looking for an extra parentheses or quote mark or what. If we put in one of these, that terminates it. That seems odd. I don't know what I missed there, but let's take deviation. Well, we'll just try this example down here and see how it works. And we get nothing back. I'm not liking that at all. Let me take this out. I'm going to take out all this too. Let's make sure all these things are paired nicely. Yeah, that looks good. Let's source that. Okay, that's a little more responsive. Calculate a deviation. That looks good. What if we try to calculate a deviation of something that's text? We get an error with an automatic error message. Nice. Let's take the deviation of something that is numeric but is very short, like we'll make a numeric vector that has no length. And again we get an error and an automatic message telling us that length x greater than 0 is not true. So convenient shorthand if you have a lot of conditions you want to trap pertaining to your arguments, or maybe relations among the arguments or something else too. Errors do not have to be just about the arguments. I was looking at the example for listings 916 and 917, and I see a very interesting error that we can demonstrate. Actually, it's not an error, but it's a vulnerability with this function. So we're going to source numerics again, just to remind ourselves what it does. We'll do numerics of theof. Grab that and run it. We find out that subject is not a numeric column, but weight, dose, time, and conc are. Now, here's the problem. That inside the loop, well, inside the function body, we wrote a loop that takes 1 to the number of columns in X. Well, you know, that works under many circumstances, but not all. Here we had a data frame, theof, with 5 columns. Does that work for a 1-column data frame? Let's try this. What if we said head of theof, and now we're going to revisit our subsetting arguments. We talked about this just a minute ago. Yes, it is possible to get a 1-column data frame out of this by saying drop equals false. There we have a 1-column data frame. So we could test numerics on that and see how things work. Actually, we don't need to say head in here. We'll just do numerics. Well, gotta fix that. I'm missing a parentheses. That looks good. And we see that subject is not numeric, as we expected. Now, the reason that works is because when you take the number of columns of that thing, and we can do that right here, you get, of course, 1. And when you create a sequence using the sequence operator 1 to 1 like this, you get back 1. And that's great as an argument to a for loop. So essentially over here we have for column in 1 to 1, that is only one column out of x. Then we do all this stuff. It basically happens exactly once, and that's fine. But what if you had a data frame with no columns at all? Now you're thinking to yourself, that would be pretty silly and rather useless. And, well, yes, in many circumstances it would be. But if you're writing complex code or building packages or other utilities, there are cases where some result might be an empty result. And instead of throwing an error, you would like your software to just quietly go on its way. And that's exactly what a for loop will do if the sequence over which it iterates has no length. It'll go merrily on its way and not bother to execute the content of the loop. That would be a great behavior to build. But you see here, if we had a data frame with no columns in it, then we could be in trouble here, because the result would come back 0, so the sequence operator would give us 1 to 0, and that means that inside our for loop we'd be first checking column number 1 and then checking column number 0, and there is no such column in either case. So you wouldn't want that to happen at all. What you'd really want there is there to be no columns at all. So first of all, let me just prove to you that there really is such a thing as a 0-column data frame. You simply can call data frame like this. Does that work? Yes. Data frame with 0 columns and 0 rows. We could even call it like this and insist that there be some rows by supplying names. I think it's row names. Now we get a data frame with no columns but 4 rows, whatever that means. Okay, so we could test numerics on that. And now we get an error that the subscript is out of bounds. We know what that is. We're looking for column 1 and there aren't any columns. Then we look for column 0. Actually, probably never get around to looking for column 0 because we have that very strange sequence in there. This is a classic situation where you actually want to generate a 0-length sequence and not assume that there's going to be a column 1. The way you can do that is simply, instead of using the sequence operator, use the sequence function. And if you redefine your function thus, you'll get the intended result. Because, well, just for example, if we say sequence of data frame, not knowing what else to do with an instruction like that, the sequence operator will take values from the length of the data frame. It'll basically expand the length of the data frame into a list of values. And here, there aren't any, so it gives you an empty result. And that's perfect for the area we're trying to trap. So we've defined data frame the new way, so now we'll try numerics. Sorry, we've defined numerics the new way. And we'll try a 0-length data frame. And we're not worried about a pretty result here. We're just interested that it not return an error. And it doesn't. It just says logical 0, nothing really going on there, but no errors. So your code can continue if there were other useful things that you wanted your code to do. Now, a little bit of trivia here. Sometimes sequence can give misleading results. So the authors of sequence provided a somewhat more reliable version that's recommended for exactly this case. It's called sequence along. Basically, it takes its values from the length of the object that you pass. You get 1, 2, 3, 4, or whatever it was for the number of elements in that value. And you iterate over those, even if there were none at all. So we could define it that way and show that it still works for the very short data frame, and it also works for something like Theof itself. And there's the result we saw before, just this time written or achieved with a function that is written more robustly. That concludes the material that I had to share with you regarding advanced function writing. We've seen error detection and argument trapping. We've seen various alert levels, and we've seen branching and for loops, controlling visibility, and also just a little bit of a taste of object orientation, an important feature of the R language. I'm going to remain here and take your questions if you have any about this chapter and the exercises, or any questions about the course in general or other chapters. And if we run out of questions, we can all leave early. Feel free to leave now if you're all set. Otherwise, stick around and see what people have to say, or offer a question or a comment of your own. I see a question. It would be nice if you show how to write a function for practical things like getting AUC. Sure, I'd be happy to do that. In fact, I've written one already, and it's in the MetroMRG package, and it's called AUC. Oh, maybe we haven't loaded that package. By the way, it's relevant. I think a couple of weeks ago, I was using the keyword require here, or the function require, to load packages, and someone asked me why I did that and how it's different from library. Turns out that require is really oriented towards authors of packages. So it's something, require is something you would use inside of a function. But if you're just conducting your activities interactively like this, it's recommended to use library. So I'm not going to use require anymore. I'm going to stick with library because I'm interactive right now. We'll load this package, and we'll see an example of AUC in here. There's the function definition. Simply clearance, a function of clearance and dose over clearance, for example. Now, that presumes something about the context. Presumes that you have a vector of clearances and a vector of doses, and you just want to do the math on that. In some other circumstances, you might actually have a data frame with some times, and you want to do a sort of a non-compartmental piecemeal calculation of AUC across a bunch of samples. And for that, we have a function written by Dr. Gibiansky that we can see in the help. And this is uppercase AUC. In this case, we see that data here is a data frame containing the data to use. And time is chronologically ordered time variable present in the data, usually just time. There's also a default for ID so that we can break this up by subject. And a column to show where we want to take our y-axis values, where we want to drive them. DV is the default because that's often what you'd be calling it in a non-mem-ready data set. So that function is there. You should know that it's available, and we can quickly show the definition of that. Slightly more complex, but we can fit it all on one screen. I'll back this down a bit so you can see it. So it might be instructive sometime to just go through this and make sure you know what's going on. That's a great way to learn R, by the way, is to look at functions other people have written and see what functions, what techniques they're using. Sometimes they might be very difficult to follow, and you might promise yourself never to do things that way. Sometimes they might make a lot of sense, and you'll start adopting those techniques. Here, for example, the first thing that's happening is that we've taken the data and we're ordering it according to ID, and we're sorting it decreasing by time. Very interesting. I would like to know at some point why it's being sort of decreasing by time. I might have tried it the other way. There must be a good reason for that. So you can go ahead and go down through the rest of the code and see if you can tell what's going on and why some of these things make sense or how they're being used. If you have a function you want to view that doesn't quite fit all on screen, you could say fix AUC, and then it should pop open in a little window for you, and you can actually mess around with things and say, let's see what happens if you sort that increasing on time, and so on and so forth. Try variants of the function, or additions, if you will. I'm going to cancel out of that because I see no good reason to change this function. It's worked very well for a long time. I see another comment. I was thinking of calculating base ID on the trapezoidal rule. Oh, calculating based on the trapezoidal rule. Yes, AUC does exactly that. The uppercase AUC is trapezoidal rule. It doesn't actually say that here, but I can verify that from, oh yes it does, right there, using the trapezoidal rule. So that's exactly what you'd want to use. In fact, I don't know how I missed it. It even says that in the title of the function. Incidentally, there are a variety of pharmacokinetic parameters for which there are already functions in the MetroMRG package. Looking for help on AUC brings up certain properties. Looking for body mass indicators or clinical indicators of various types, like BMI, brings up a list too. Be aware that they're there so you don't spend a lot of time rewriting functions that we've already done for you. There are also other packages on CRAN that provide pharmacometric material and functionality. One of them is PK something. I don't remember exactly what it is, but we could go look for that. Well, there are 16 matches to PK. Basic non-compartmental pharmacokinetics. And PK fit, PK graph, PK report, PK tools, PK DA class, etc. PK model finder, interesting. And I wonder if that's all of them. Pop PK, summary of population pharmacokinetic analysis. Very interesting. Not familiar with it myself. RGL-PK. I think that's more programming kit. And that probably is similar. So the interesting examples are this one and those. Can you quickly show how to use the AUC function on the Theof dataset? Sure, that's an interesting assignment. Let's make sure I understand the help here. If I have args AUC, I need data, time, ID, and DV. So let me look at head of Theof. I see that I have not ID but subject, and not uppercase time but title case time, and not conc but DV. So I guess I would do something like this. Time equals time. ID equals subject. DV equals conc. Now you've got one area under the curve for each subject. That's a very efficient summary. It'd be also nice to plot those. What will we do? XY plot. Maybe concentration versus time by subject, where the data is Theof. You know what? Let's make that type equals lines. And now you get a more visual representation of what that AUC might be indicating. For one thing, I would guess that subject 12 would have a bigger AUC than 6, and indeed that seems to be the case. Remember that this technique is limited by the assumption that you have a full profile of measurements. It's not only sensitive to the density of the measurements, but also the duration. In the tails of the profile, maybe you don't need a lot of data points, but you should wonder if you're getting back down to baseline or back down to trough, or if you're anywhere near, say, 5 decay half-lives, to know whether or not you're adequately representing the full profile for a clinically meaningful duration. Let's see what we have for times in Theof. We have 78 unique times, but they're probably tightly clustered. I might do this, plot Theof time versus Theof. Well, let's just make it X and Y. And let's try to round these a little bit. Yeah, they're tightly clustered. You can see that there is a nominal time that was being targeted, like out here's something like 24, and some of those samples were just before the hour, and a lot of them ran late. But it gives you a good idea about the profile. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 or so sample events. And we probably see that in the documentation for Theof, if we bother to look at it. Yeah, concentrations were measured at 11 time points over the next 25 hours. The reason why it only looks like 9 is because the early time points are at a much more closely spaced to each other. So when you round them, you don't see as many distinct intervals or as many distinct groupings. We could have said round, but I said snap because it gives us more flexibility than round. For snap, we could say, let's try to round these guys to the quarter hour. I think that would do it. Yeah, now we get more groupings, although they start to fuzz into each other a little bit down there. But there seem to be more distinct groupings. I guess the way they would look would be this way. 1, 2, 3, 4, 5, 6, 7. Now it only looks like 8. I have to think about what's going on there. Let's see, snap has a rule, and rule is a vector of candidates, of time candidates, or a single value giving an interval on the real number line. Let's look at these values. Looks like there's something around a quarter hour, maybe a half hour. And probably there was a sample around 15 minutes. You could probably guess the rest of them and force them to be in that category. Why don't we try this? Let's let the rule be 0.25. We'll take samples at the half hour, at the quarter hour, at the half hour, and then at all the rest of the hours, 1 through 24. Well, that's not going to be all the hours, but just an easy way of looking at hourly samples, looking for hourly samples. Could not find function rule. Oh, I know. I need to say rule equals. Now I probably have one too many parentheses. Yeah, I think that gives us the granularity we were looking for. Yeah, it looks like there are now 11 groupings. Are there any other questions? Seeing none, I'm going to go ahead and end the lecture at this point. And I thank you for your participation. We'll see you back here next Tuesday for a continuation of the course. I'm not sure what we're going to do about the sequencing of chapters because I know we missed one, but we can make that clear through offline discussions. Thanks.